Everybody, let's talk about energy bar charts and how we're going to convey how the energy of our system is changing. Okay, at the core of this conversation is something called the law of conservation of energy, and I know you've learned about it in previous science classes. So what the law of conservation of energy says is that energy is neither created nor destroyed. It is transferred from one object to another or from one form to another, but your energy is never actually destroyed. And so if we have my ever-present cup of coffee here that's nice and hot, if this is going to cool down, that energy is going to be transferred from the cup of coffee out into the surroundings. It's an exothermic process if the cup of coffee is our system, and however much energy that cup of coffee lost, the air and the counter and the surroundings gained that same amount of energy. It didn't gain more, it didn't lose less. We have an equal transfer. Something gained the energy and something lost the energy. Our goal is going to be able to communicate how much energy has been gained or lost by our system. And we're going to focus on the system. And we're going to be doing this in a couple of different ways to convey this information. The one we're going to be focusing on most here are LOL energy bar charts. We're going to follow that up with some phase diagrams along with particle visualization. So lots of ways to express what's going on, looking at it from slightly different angles. So let's talk about what goes into an LOL energy bar chart. They're called LOL energy bar charts not because it is hilarious, but because they look like an L, an O, and an L. So what we have on the left is a axis that we're going to turn into a representation of where the energy was before whatever change happened. We have a circle in the middle that's going to represent our system and what is changing. And then we have an axis on the right that's going to show us what happened afterward. Now, as we look at this, this circle in the middle, like I said, is going to be your system. And so you're going to label this with whatever the system is. I want you to say what it is. Maybe it's my cup of coffee. So you're going to label your system. On the left, you're going to demonstrate what you're starting with. So what the initial thermal energy of the system is and initial phase energy is. Now, these are going to be represented with as blocks. So yeah, there's kind of like a number of blocks, but this is very qualitative. As we're working. So our thermal energy will be the energy of motion or a measure of the temperature of our system. The EPH is the phase energy. So this is talking about the state or the spacing of the particles. And what we're going to be able to do is make some generalizations. When something is cold, it's going to have relatively low thermal energy because those particles are moving slowly. And so if something is cold, perhaps we would represent that with 1 or maybe 2 blocks on the bar chart. So that'd be very cold, maybe a little less cold. And then as we increase the temperature, you're going to add additional blocks. For sanity's sake, we're going to keep our options at 0. Never going to happen unless we're at absolute 0. So 1, 2, 3, or 4 blocks for our thermal energy conversation. So if you're down at the bottom, things are colder, there's less thermal energy. As you heat it up, your thermal energy would be increasing. So the more blocks you show, the higher the temperature for that thermal energy portion of the chart. The phase energy is going to be about the state. And so if we have 1 block of phase energy, we have relatively little potential energy. So that'd be for a solid. If we have 2 blocks, that's more. So let's go for a liquid. When you go from a liquid to a gas, there's a huge change in space, and so a big jump in the potential energy. And so gases have more potential energy. My boxes got bigger. That's okay. Gases have more potential energy, and so maybe we'll give them 4 blocks. Again, it's about gaining and losing when we start doing this conversation. So just think, is there a lot, is there a little, and reflect that with your bar chart. When things change, we were going to show that. So this is really hot gas, what I've drawn as my before situation. Maybe we're going to cool it down. So maybe it only ends up with 2 blocks worth of energy. And maybe we're also going to cause it to condense. So it went from a gas to a liquid, and that means you'd only have 2 blocks worth of phase energy when you were done. So what we can see with this LOL chart is we can see where you started and where you ended. And then if you look at this, at the beginning there were 8 blocks of energy, and at the end there's only 4. That means the system must have lost 4 blocks of energy. And so you are going to show on that system circle that there is energy leaving, and that there were 4 blocks of energy that left. And in this way, we're providing a nice summary of what was the energy when we started in terms of thermal energy due to the motion of the particles, which we can use our temperature to get a kind of feeling for. What was the phase energy? And then how did that change, and what did we end up with on the other side? So those are going to be the core pieces to an LOL bar chart. Okay, so LOL bar charts are our way of expressing what's going on, and that's very much what we're inferring is happening. It's not what we're actually seeing. Heating and cooling curves, though, those show us what we see in lab in terms of how temperature changes as we add heat or remove heat. So as you look at these heating and cooling curves, we made one in lab the other day, you will see that on the x-axis is either energy added or energy lost. And so this will be referring to either an endothermic or an exothermic process, depending on whether you're adding energy in or you're removing it. You need to think about what the process is and decide what the appropriate label for that x-axis is going to be. Make sure you're including units, so energy is in joules, so put joules down there. And then the y-axis is going to be the temperature. And since it's a lab measurement, we're going to be using degrees Celsius for this. And so what you see with these phase change diagrams and the heating and cooling curves, is you see where you have a temperature change associated with adding energy. And that's where there's a slope to the line. So you've got a positive slope to the line. You'll also see where the temperature stays the same even though you're adding energy. And that is where you have that energy going into separating the particles. And so those plateaus are associated with phase change. And this pattern of a slant line means the temperature is changing, a plateau means the phase is changing, is seen in both heating and cooling curves. And so if you look at the second of the cooling curve, or the second of the curves that I put on here, this one's a cooling curve, the temperature is going down. And this one has 3 different regions where the temperature is going to change, and then 2 regions where the phase is going to change. So this would correspond to a gas turning into a liquid, cooling down, turning into a solid, and then cooling down further. And so these heating cooling curves give us a snapshot into lab for what we would actually expect to see happening for those temperatures.